And our idea here in Darmstadt is to print such a 3D structure on a flat glass, on a semi-finished product, and to create new glass joinings, glass joinings, such a point fixing here you can see in the facade, or some reinforcement on flat glass. And so we can create some advantages, like we can create a homogeneous geometry and the connection in a desired geometry for some individual products. And so we can increase also the transparency in the facade, and we can stiffen it. And you have also the possibility to reduce the plastics inside, because plastics are not so good because of UV, long lifetime of some facades. Here we have the problem of aging. And so we can avoid this, and we can create from a boring 2D structure, 2D structure, 3D structure, and also as a colored structure. And so we can bring, with the technology, additive manufacturing, we can bring the function and the design together to create such new products you can see here. There are different methods, more or less available. I think you are very familiar with these methods, but it's not all possible to print glass. There are fused deposition modeling on the one side. There are some research groups, Micron 3DB and Swarovski. There's an action also the MIT and QCell, and they use this technology to print such structures, but it's more or less for interior stuff, like arts, for example. And there's a group in former times at the KIT, now it's in University of Freiburg, and the startup Class Omer, and also the ETH Zurich, they developed out of stereolithography a possibility to print 3D structures out of glass, very thin, very tiny. They used here quartz glass. It's very expensive to do this, and they can create very cool structures, but it's not possible to use this for the built environment because they are too tiny and the technology is limited. Here you can see an overview. I don't want to get too much in it of the different technologies which are more or less available for 3D printing of glass, and what are the possibilities and the pros and the cons to this. And if we print with fused deposition modeling, yes, we will create a rough structure at the surface. This is a disadvantage, but we don't need really a pre-finishing, and we can create very fast, very big structures. If we look to other processes, so we can create with stereolithographies also not so rough surfaces, very cool one, but we had a lot of problems with the shrinkage because of the debinder ring. And this makes it very difficult and challenging. Okay, let's talk about the constraints and what we have to think, or what we have to recognize if we use glass as a structural material. On the one side, glass is very strong. If you look to the compression, we are here in a range of 1,000 Newton per square millimeter in the compression strength. But you know it, glass is brittle, and the flaws are critical on the surface. And if you bring tension on it, or like bending, it's not so good. We are here in a range of 15 Newton per square millimeter. This is a factor of 20. There's a difference in this material. Then we had also the problem during the production, residual stress. Here you can see it with polarized lights. You can see here the colors. There's residual stress, and it's not controlled. You will see a crack if the residual stress is too much during the production process. And sometimes it's not possible to anneal the things, and if the structures are too big, like this cube here, it's more or less 1 meter by 1 meter by 1 meter. They use, or you need a lot of time for a annealing process, and if this not good managed, you will see here some cracks, and this is not so cool if you think of an overhead glazing. So let's talk about the temperatures. We are in a range of over 1,000 degrees for our production, not like plastics. Here we are in a range of 200, 300 degrees. And here you can see a diagram viscosity against the temperature for different types of glass. We want to deal with the soda lime glass, the normal window glass here, and we are here in a range for our production to join the glass together, often the flat glass, in a range of 820 to 1030 degrees. And if you look to quartz glass, here in a range above 2000 degrees, so it makes no sense for us. And on the one side, we need temperature to bring the things together here for a joining process to transfer the loads. On the other side, if the temperature is too long, too high, we will create a not so cool structure. We will create a 3D structure, and if it's too hot and too long, too hot, we create also from the 3D structure a 2D structure. And so this is a challenging effect. Here you can see on the left, on this side, a very line on the flat glass, 3D printed. It looks very well, but if you look in detail here, the connection area is very tiny, so you can't transfer no loads. If you look to this sample, it looks not so nice, but the connection area is much bigger and you can transfer some loads. This is a challenging factor. And if you look to the strengths, on the next slides, you will see a cross-section out of such a sample. Here you see the glass base plate, and here a colored glass rod, and here the interface of both. And here you see the scale, and you see, okay, there's more or less, or there's no gap between. Also here you can transfer loads, and we carry out an indentation test with a Vickers diamond, and there we create some cracks, and the crack goes through this interface here, and so you see, okay, here we can transfer loads. It's a homogeneous connection. This is the other sample. Here you can see we did the same. Here you see really a gap. Here you see the indentation points or dots, and here we create also in this area a lot of damage. So it's not useful to transfer the loads. And to bring this in a process, it's challenging. There's a big team behind me to do this. We need such a chamber because we can't print. We can't print on normal air temperature. We needed a chamber in a range of 500 degrees. We had the kiln to use also waste glass, heated up in a range of 1,300 degrees. Okay, thanks. And bring it out in this chamber with a heated nozzle, and so we can create such a structure. And we use a special torch to this for the connection of the joining area. This is our machine. It's a prototype. Now we had some challenges with one furnace, so it stops now a little bit, and we hope next month we can work harder on this topic. And we look also, if we print some samples, to the safety conditions for the civil engineering. Here we speak about lamination processes and also pre-stressing of such samples. Lamination process, we did this with such a 3D printed structure. We laminated this here together. It's a work of Amir and the LZH Hannover. Here, bring it together in a dimension of 500 by 500 millimeter. Last year, you can see it was also here at the beam, and this is possible with our machinery. Okay, with this technique, we can create such new glass joints. You can see here you see the conventional stuff with adhesive, with boreholes. Borehole in such a brittle material is not the best idea, I would say. So we can create such a structure with the 3D printer and mount here such a point fixing, and it helps us to avoid boreholes in the facade. And here you can see the structure from last year we presented here. This is in general possible to do so. The other thing is for reinforcement. If you look at, glass is driven, large glass samples in the window are driven more or less by the deflection. Glass is, because it's thin, and the bending behavior with a thin structure, you can see this. And if you fold this this paper and print some, for example, some ribs on it, you know what happens. You can stiffen, and so the structure, and so you can stiffen like such a cross here on such a plate. Here's the cross section, or in this direction. Here it's also created with some molds and other possibilities for design aspects. You can create such a structure and stiffen. You can reduce also here the weight and also the footprint to this. And in the end, you can create also such sandwich panel with 3D printing with such a lattice structure. This is also in general possible to do so, and also for some linear bearing in the facade. Here are some samples. Some samples are also here. What we create, it's a feasibility study. We bring some ribs on it to stiffen it. And so we can, for example, we can reduce here the weight of such a sample. If we had a span length of 2 meters of such a glass plate and a surface load of 1 meter and with a width of 1 meter, we need 12 millimeter or more than 12 millimeter for the criteria of deflection thick glass. And if we bring on 6 millimeter thick glass, 6 ribs in the dimensions of 40 by 10 millimeter, so we can reduce the weight more or less than 40%. And if we increase here these values, we can reduce more. Also here we have the possibility also for sustainable issues. I want to sum up. It's challenging because of the brittle material behavior, the residual stress, and the high temperature, but it's feasible. And now the next step is we want to print on larger structures in the dimensions with the new 3D printer of 500 by 1 meter. And our vision is to print in the dimensions of such a flat glass of 3.25 meter by 20 meter. This is our vision, not tomorrow, but in the next years. And so we can use also waste material. We can drink a beer today and throw it then in the printer, and we can create a structure on it. It's also an issue, also not to drink, also to drink beer, yes, it's also an issue together, and have some new ideas to it. And we think also about the safety requirements for the building environment. This is also very important for us to bring it in the structure, not only in the living room. And we can bring also new functions to it, design, color, and also light aspects. And so we can create such samples. And so in the end, we bring with AM also for the other materials the function and the design together and create new stuff. Thank you for your attention. I hope you can enjoy. And if you have questions and demands, please ask me. Thanks.
Questions for Matthias? I have a question, maybe to start with, Matthias. Thank you so much for that presentation. It's really amazing to see. And maybe I'm remembering that maybe when it is molten or hot, glass wants to have a specific thickness. It wants to be about 6 mil thick. Mm-hmm. And I'm wondering, does 3D printing give you a way to move around that, to have thicker sections, for example, or thicker thickness? Or are those kind of other, the other sort of learnings from other glass practices, are they something that you're able to bring in to to the digital manufacturing process of glass?
Yes, we have worked here also with some guys from glass manufacturing. Glass maker, they mold glass for their knowledge. It's very important, and also bring also the guys from the handmade process together with the guys from the informatic for the digital things, to bring all two disciplines together to create new structures. And this is really important, and not to do this by our own. It's not possible for me, as I'm only a civil engineer, to create such a work alone.
Yeah. It's also interesting what knowledge can be transferred from, say, a crafts practice to to a fully mechanized practice, so you know, or one particular technology.
Yeah, it's also especially we had a gap in the future for the workers, and so this is really a problem in the industry, especially in Germany. I don't know in other countries. I think the same, and so we can use such digital machines to create such structures and not handmade one, because we had no workers to do this.
Yes.
I'm not a little bit extra, but in one of your slides, I believe it was 13, you showed me this, this ribbed concrete floor slab, which is the design principle being only compression only, right?
No, it's a plate. This is a plate. It's for bending stuff.
Okay. Well, I think in Zurich they make these plates which are compression only. I'm always fascinated by this 1000 megapascal compressive strength of glass. Do you envision glass being more widely adopted as a structural building material? Or?
Nowadays is structural material, but if you look to the glass facade on slide number 3 or so, to the Chanel, it works as a structural material. And yes, we have to optimize the structures. We have to avoid bending, more or less, to come, you mentioned, to the such arcs, for example, to use this, and so we can activate the compression strength and avoid the tension. And this is a good idea, yes, and for optimization process. Also, we have to do this.
One last question.
Thank you very much, Matthias. Very nice presentation, very interesting. I think the safety issue is something indeed that is difficult to solve, but I'm curious how you will do that. My question is actually, do you also envision printing of glass for repair rather than reinforcement, but if you have a damaged panel or...
In general, I would say at the moment, it's not possible because in practical you can't go in the facade and print because you have to heat it up. If you have quartz glass, yes, it's possible, but not with soda lime glass because of the temperature differences, and then you will see the cracks.
But if you're able to take it off the facade, I mean, so
yes,
reuse and
this is but you have to bring a temperature on it, and this makes it very difficult because we are here in a range of 500 degrees for the rest of the sample to the joining area. Also this, I think now I would say no, but we can think together to this topic.
Okay, thanks.
Thank you very much.